Okay, so what I'm going to do now is, in continuation with our discussion on the importance of local rings, I'm going to explain the notion of non-singularity, okay, which is in analytical language, classical analytical language, you're trying to say when something is a manifold, okay, so or when something is smooth, okay. So the so in other words, the idea is that an object is smooth at a given point if the dimension of the object is the same as the dimension of the tangent space at that point. Usually what happens is that the dimension of the tangent space will be more, and if the dimension of the tangent space is more at a given point than the dimension of the object that you are studying, then that point is a singular point, it is not a smooth point. So for example, its smoothness in terms of in the language of classical or in the language of analysis. So if you take a if you take a surface and you take a point on the surface, then the surface is, so suppose you are looking at the usual topology, okay, and you are in Euclidean space and you look at a surface, for example surface of sphere or surface of cylinder or whatever it is, okay. Then if you look at the so there is a dimension of the surface which is say m, okay. So if you are if you are looking at a surface in, if you want in so if you are in R3, okay, real Euclidean space and you are looking at a surface, it will have dimension 2, okay. A curve will have dimension 1, alright. So a surface will be dimension 2, a curve in 3 space will be dimension 1, and you, if you take a point on the surface, alright, and draw, you try to draw all possible tangents to the surface at that point, you get the tangent space at that point. And if the surface is smooth at the given point P, okay, then what happens is that the tangent space will also be 2 dimensional, okay. So what will happen is that you will get a unique tangent plane, you will get a unique tangent plane at the point P, okay. And if the surface is not smooth at a given point, what will happen is that if you look at the tangents, the tangent space could have higher dimension. So for example, if you take something like a cone, and if you consider the vertex to be the point, okay, then what happens is that if you how do you calculate the tangent space? It is a space spanned by all tangent vectors. And what are tangent vectors? I mean these are they lie on tangent lines passing through the point, okay. So you know, if I try to draw tangent lines passing through this point, I can easily draw three I can easily draw three linearly independent vectors. I can draw three different lines which lie in the directions of three linearly independent vectors, okay. So you know, if the cone is like this, right, I can draw one like this, and then I can draw one like this, and then I can draw one like this, okay. So I can easily draw three of them. I get three linearly independent vectors, and therefore you know, if you take all such vectors, the space that they span will be R3. So you know, tangent space here, this is the vertex of the cone, has tangent space isomorphic to R3 as a vector space, because you are easily able to find three linearly independent vectors, and you know, and these are vectors in 3 space, alright, and therefore the subspace that they span will be all of 3 space. So what happens is that so here the dimension of tangent space at the point P is 3, which is greater than or equal to 2, which is the dimension of the surface. The cone is 2 dimensional, but you take that point which is the vertex of the cone, there you look at the tangent space, namely the vector space spanned by all tangent vectors. The tangent space is 3 dimensional, so the tangent space dimension is more than the dimension of the cone, and so this tells you that P is a singular point. P is a singularity or singular point or a non-smooth point. Sometimes in classical, I mean in analysis, in the language of usual analysis, you also say it's a non-manifold point. It's also called as a non-manifold point, alright. So the idea is that at any point, if you want to check whether it is a smooth point or not, okay, what you do is that you try to measure the dimension of the tangent space at that point. If the dimension of the tangent space is equal to the dimension of the object, the dimension of the space on which you are considering the point, then the point is a smooth point. Otherwise the dimension could very well be more. If it is more, then the point is not a smooth point, it's a singular point. So it's also the case that's also the case with a line, I mean with a curve. See, if you take a point like this on the curve, then you know, if it's a smooth point, I'll get a unique tangent direction to the curve at that point, and the tangent space will just be a single line. It will just be the line spanned, it will just be the space spanned by a single vector. So you see the tangent space, you will get a unique tangent line. You will get a unique tangent line at the point P. The tangent space at the point P has dimension 1, and that is equal to the dimension of the curve on which the point P is lying. That tells you that the point P is a smooth point, okay. But however, you know, if I take a curve which is not a smooth curve, then things can be different. For example, you know, if I take something like you know, on the plane, I can easily draw a curve which is not smooth. So you know, for example, if I purposely draw something like this with a kink here, if I draw a curve like this and take this point, then at this point, if you calculate the tangent space, you will easily see that you can draw 2 tangents, you know, if I approach from the left, okay, I will get a tangent like this. If I approach from the right, I will get a tangent like this, at this point, okay, and these two are two linearly independent directions, therefore the dimension of the tangent space at this point is 2, whereas the point is lying on a curve which is one dimensional, so the dimension of the tangent space is more than the dimension of the curve, the dimension of the object on which the point lies, and that tells you that that point is not a smooth point, okay. So here what happens, again P is a singular point as the dimension of the tangent space at the point P is 2, which is strictly greater than, so here also I should not put greater than or equal to, in fact I should put strictly greater than, 3 is strictly greater than 2, and here it is 2 is strictly greater than 1, which is the dimension of the curve. So this is the curve on which the point is lying, the curve is one dimensional, okay, but the tangent space at that point is 2 dimensional, where the tangent space dimension exceeds the dimension, these are the singular points, okay. So this is what happens in so I have of course looked at dimension 2, dimension 1, you can therefore say if you are looking at an n dimensional hypersurface, okay, in say some which has to be thought of in some Euclidean space of dimension greater than n, okay, then at a point how do you say the point is smooth or not? What you do is that you check the dimension of the tangent space at that point. If it is strictly greater than the dimension of the space on which the point lies, then it is not a smooth point. If it is equal, then it is a smooth point, okay. So this is the idea from at least from calculus and geometry, usual analysis, okay. Now the analog for this in algebraic geometry is of course there, and everything is I mean this business of estimating the this business of calculating the tangent space and its dimension at the point P is done by looking at things connected with the local ring at the point, okay. So here is a definition. So now I'm switching from some classical or analysis based situation, I'm going from there to algebraic geometry. So so I'm going to take the following thing, I'm going to define when a point of an affine variety is smooth, I mean when it is non-singular, okay, and when it is singular, right. So here is so in algebraic geometry, so how do we do it? So what you do is that you take X to be an affine variety, okay, let X be an affine variety, P a point of X, okay. How do you define that P is a smooth point or a non-singular point, okay. So for that what you do is you do the following thing. So let X sit inside some an affine space over K is of course an algebraically closed field, X is an affine variety, so it is an irreducible subset, it is isomorphic to some irreducible closed subset of some affine space. So this is by definition X is isomorphic to an irreducible closed subset of affine space, okay, and then you have the ideal of X, which is the ideal inside the affine coordinate ring of an, okay, which is actually well, it can be identified with the polynomial ring in n variables if you want. Okay, if you take capital X1 through capital Xn to be the coordinate functions, then you take the polynomial ring in those coordinate functions, that is the affine coordinate ring of affine space. Okay, and X is an irreducible closed subset, so it corresponds to a prime ideal, so I of X is its prime ideal, and of course you know the affine coordinate ring of X is given by the affine coordinate ring of affine space, namely the polynomial ring mod the ideal of X. There is a finitely generated K algebra which is an integral domain. Okay, but the point is more importantly, the point is about this ideal. See, the ideal of X, this is an ideal in this polynomial ring which is a Noetherian ring, so it is finitely generated. Okay, so let us look at a set of generators, so F1 say G1 etc up to Gm is ideal generated by finitely many polynomials. Okay, this is true because in a Noetherian ring any ideal is finitely generated, and the polynomial ring is Noetherian because that is as you know Hilbert's basis theorem, or I mean Noether's theorem. So you choose a set of generators, alright. Now what you do is you do the following thing: you calculate the Jacobian of this m tuple of functions with respect to these n variables. Okay, you get an m by n matrix of polynomials, a matrix with polynomial entries, and that you evaluate at the point P. Okay, and then you get a numerical matrix, a matrix with the entries in the field, and calculate its rank. Okay, so this is the thing that you will have to do. So you calculate rank of Jacobian of G1 Gm with respect to Jacobian with so it's with respect to these variables. So let me just write it like this: calculate rank of the Jacobian of all this at the point P. Calculate this number. Okay, so what you're doing is, well, basically what you're doing is you're taking G1, partially differentiating it with respect to X1, and then you know evaluating it at P. Okay, and then you do it so on with G1 with respect to, well, all the variables Xn, and then now you repeat it with G2 with respect to X1 at P, and this is dou G2 at Xn at P. Okay, and then you do it like this. You calculate this, you have this matrix. Okay, now mind you, when I say partial derivative, you don't have to think of derivative in the sense of calculus, because derivative in the sense of calculus will require a limiting process, but don't think of it as derivative in the sense of calculus, but think of it as formal derivative, because you know you can always take any polynomial in so many variables and you know how to define the derivative, okay, using the usual rules of formal rules of differentiation. So in calculating these derivatives there is no need for I mean you are not actually computing derivative in the calculus sense, okay, but you are directly using the formula for the derivative, which, so you know formulas for differentiation of polynomials can I mean these are the same formulas that you get in calculus, but then they make sense even without calculus. You take those differentiation formulas as the definition rather than getting them by using a limiting process. Okay, So you have this matrix, okay, this is a matrix, you calculate its rank, okay, and what you do is you do the following thing. We say P is a non-singular point of X if, so this is a definition, the rank of the Jacobian of the generators, okay, of the ideal of X at the point P should be equal to the codimension of X in AN. And what is codimension? It is, codimension is just dimension of AN minus dimension of X, so it is just n minus dimension X. So codimension of a subspace is just the difference of the its, you take away the dimension of the subspace from the dimension of the ambient space, okay. The ambient space here is affine space AN, the subspace is X, okay, which is embedded sitting inside AN, and you take the dimension of the ambient space minus the dimension of X, that is called the dimension of the bigger space minus the dimension of the smaller space is called the codimension of the smaller space in the bigger space, okay. So the condition for P to be non-singular point of X is that the rank is equal to the codimension, alright. So this is the condition, and by the way, rank of the Jacobian at the point P is actually rank of this matrix, okay. So this this is equal to n minus dimension of X. So this is the condition for P in X to be non-singular, or for it to be a smooth point, okay. Now the beautiful thing about varieties is that, you know, they are not always smooth, okay, they will involve singularities, but the point is that where the set of points which are singular will form a very small subset, where if you take the set of points which are not singular, that will be a huge open set, it will be a dense open set, okay. So you know, if you want to compare a variety with the classical smooth object in a smooth object in analysis, okay, the comparison should be if you want to think like that, what you should think of is that a variety is something like a smooth object on an open set plus a boundary which is the complement of the open set which will have singular points. So you know, something like a cone, okay, if you throw away the point which is the vertex of the cone, the rest of it is all smooth, okay, and that is a dense open set, and the boundary is this point which is a singular point. So a variety also looks like that, there is a big open set which is full of smooth points, okay, where it is like a smooth where it is the analog of a smooth object in analysis, okay. These are all the points where the dimension of the variety is the same as the dimension of the tangent space, okay, and that is what is actually being said in this definition, but then we'll unravel these definitions and try to literally see that this is the same as that, okay, but there is some translation that one has to do, okay, which we will do, okay. So when you think of a variety, what one needs to remember is that there is an open set, dense open set where it is smooth, okay, where it is like a manifold, a smooth object in analysis, and then the complement of the open set is a closed set, it is the boundary, and that closed set will consist of singular points, okay. Of course there could be varieties which are totally smooth, that also can happen, and such varieties which are totally smooth are called non-singular varieties, right. So now let me so this definition looks a little involved, okay, but the advantage of this definition is that you can make you can do some calculations, okay. So for example, so if you want to apply it, so let me take the example of hypersurface in AN. Okay, what is a hypersurface? It's a codimension 1 subvariety of AN. It's a codimension 1 subvariety, and we have seen this. A codimension 1 subvariety means that it's an irreducible closed subvariety of dimension 1 less, so it's dimension n minus 1, and we have seen that this will happen if and only if the ideal of the variety is generated by a single non-constant irreducible polynomial, okay. So so if I call that as x, let me call this as x is equal to hypersurface in AN. So ideal of x is generated by f, where or let me use G itself, G an irreducible non-constant polynomial. So we have seen this, and now what is if you take a point P on this hypersurface, when is the point P smooth? So if I apply this condition, so I will have to look at rank of the Jacobian of G, which will be just at the point P, and that's just going to be, that's equal to rank of 2G by dou x1 2G by dou xn. Okay, so you are just looking at all the first partial derivatives of that polynomial, and then you are evaluating them at a point P, and this is equal to the codimension of x, and what is the codimension of x is 1, okay, because x is a hypersurface, so the codimension is 1 if and only if P is a smooth is a non-singular point of x. So if you want the hypersurface to be non-singular, that means you want all the points on the hypersurface to be smooth non-singular points, then the condition is that all the first partial derivatives of G should not simultaneously vanish at any given point, okay, and such a polynomial is called a non-singular polynomial, okay, it's called a smooth polynomial. So x is non-singular, x is non-singular if so x is non-singular means x is every point at every point of x is non-singular, that's what it means, okay. So x is non-singular if and only if the rank of this is always 1, okay, and that means that given any point at least one of the partial derivatives should not vanish, okay, at least one of the partial derivatives dou G by dou xi never vanishes, does not vanish. At each point of x, okay. So it's very easy to check that a hypersurface is is non-singular, that it is smooth, right. So examples of these things are, well, examples of smooth I keep using the word smooth, but in algebraic geometry the word smooth is reserved for something more general than this, so the word that we use is actually non-singular. So examples of non-singular hypersurfaces are, well, hyperplanes which are given by f is linear homogeneous. F is need not be homogeneous, well, f is just a linear polynomial. You take a linear polynomial, right. So that is f of so f of x1 through xn is just sigma alpha I xi minus some beta 0 I equal to 1 to n, something like this. And of course I am not looking at the case when all the alpha i's and the beta and this beta are all 0. I mean so I really want a linear polynomial which is not the 0 polynomial, right, or a constant polynomial. So at least one of the alpha i's survives, is non-zero. So if if a certain alpha j survives, then dou f by dou j, if I take the partial derivative of f with respect to xj, I will get the alpha j which is not 0. So that will never vanish at any point on this hyperplane. So these hyperplanes are non-singular, and then you can take things like n equal to 2, and you can take f to be x squared plus y squared minus 1, okay. Then well, this is the circle in A2, this is a circle in A2, and if you calculate of course I am taking the variables as x and y, okay. Well, if I want use standard notation, I should take x1 and x2 right. So let me do that. Let me write it as x1 and x2. Then you see if I calculate dou f by dou x1, dou f by dou x2, I get this, I'll get 2x1, I'll get 2x2, okay. And now now you want that at any point of the circle, okay, one of these should not vanish. So when will both vanish? Both will vanish at the origin, okay. Both will vanish at x1 equal to 0, x2 equal to 0, which is the origin in A2, alright. But then the origin is not a point on the circle, so it does not give me, so what it tells me is that this is not going to vanish at any point on the circle. But there is a catch. The catch is that there is one issue, this K could be characteristic 2. K could be an algebraically closed field of characteristic 2, in which case this will be identically 0, because in characteristic 2 is 0. So if K is an algebraically closed field of characteristic 2, then this x1 squared plus this will become this will vanish. So you have to be careful about the characteristic of the field where you are doing these computations, okay. And so let me put characteristic is not equal to 2 for safety, okay. So whenever you get these some integer coefficients, you have to really worry about whenever you are talking about something vanishing, okay, and you are in algebraic geometry, you are working on an algebraically closed field, you should remember that it could be any characteristic. So if the characteristic divides one of these coefficients, you are in bad shape because it will just vanish, okay. So if you take characteristic not equal to your circle is smooth, and well, in fact if characteristic is 2, something more serious is happening. F is first of all not irreducible. If you are in characteristic 2, this is the same as x1 plus x2 plus 1 the whole square, because in characteristic P, a plus b whole power p is a power p plus b power p. Okay, so you know x1 plus x2 and minus 1 is the same as plus 1 in characteristic 2. So this is actually, f becomes square of a linear polynomial in characteristic 2, it becomes x1 plus x2 plus 1 the whole square. Okay, and so it is not even irreducible. Alright, so you have to worry about characteristic. Alright, of course if you are working over complex numbers one does not worry about these issues, but then whatever algebraic geometry we are discussing about is over an algebraically closed field, and you know you can have algebraically closed fields of any characteristic, right. So so this is not equal to 0 for any p in the 0 set of F, which is a circle in A2, and well now you know you can start this is with one equation you can start looking at objects given by several equations, okay, and start checking which are the points that are smooth points, and whether the smooth points, that is the non-singular points, are all the points, or you get some points which are singular, some points which are non-singular. So that way this definition is useful for computation, alright, but you know the problem with this definition is that there are two problems with this definition. So the first problem is I only defined non-singularity for a point of an affine variety, okay. I have not defined non-singularity at a point for any variety, because any variety in general could be non-affine, okay, it could be quasi-affine, it could be projective, it could be quasi-projective. So well but anyway I can get over this problem by saying that, well, I know that any variety is covered by finitely many open sets which are isomorphic to affine varieties. Therefore you give me a point on any variety, I can find an open set surrounding that point which is isomorphic to an affine variety, so that point is now lying on this open set which is an affine variety, and then I can say it is non-singular or not based on this definition, alright. So I can get over this problem of extending this definition of non-singularity to any variety, just because of the fact that any variety admits a cover, finite cover by open sets which are isomorphic to affine varieties. That's an issue that's easily resolved, but that's something more serious. The more serious thing is this numerical business here. You see there is a lot of ambiguity here. You see the same affine variety could be embedded in different affine spaces, okay. I could embed this same affine variety in AN, I could also embed it in some AM. If I embed it in a different AM, then the ideal will change, okay. So this ideal depends on the embedding. See, this ideal of X is the ideal in the affine coordinate ring, and that affine coordinate ring it is an ideal of the affine coordinate ring, it is an ideal of the affine coordinate ring of the affine space in which X is embedded. But if I change this affine space where X is embedded, then I am changing this ring, therefore this ideal also changes. This ideal is not an invariant. See, what is an invariant? This is the only thing that is an invariant. For an affine variety, the affine coordinate ring is an invariant, okay. Whether I embed X as an irreducible closed subvariety of AN or AM, any affine space, if I calculate this, if I calculate the affine coordinate ring of X, then you know that is an invariant, because that is also equal to OX, the ring, you know, the regular functions on X, but the ideal can change, okay. So there is an ambiguity of the embedding. If you change the embedding, the ideal will change, alright. That is the first ambiguity. What is the second ambiguity? Second ambiguity is here when I write the ideal I write a set of generators for the ideal. The same ideal can have different sets of generators. The sets of generators are by no means unique, okay. So if I change these generators, then this this Jacobian matrix itself will change. Instead of, well, even the number of generators I do not know. G1 through Gm may be one set of generators. I may find these are m generators, I may find some different number of generators, and they may be all completely different polynomials, and again I do this computation. What is a guarantee that my definition is consistent? Okay, for the same ideal, if I keep the same embedding and therefore my ideal is fixed, if I take a different set of generators, what is the guarantee that if I compute this I will still get the same rank? So, well, thanks to God that is the case, okay. And the point is, why does that happen? The one way to see it is using the language of local rings, okay. So this is where the power of local rings comes in, to tell you that this definition is independent of the embedding, it is independent of the generators for the ideal that you choose. You will this definition is absolutely correct, it is not going to fail you, it is not going to become inconsistent, okay. So it is to that end that I am going to state something now. So here is this is a fact which was discovered and proved by Oskar Zariski, who can very well be called the father of, or even the grandfather of algebraic geometry, the grand man of algebraic geometry. He was a person who initially wrote papers in the Italian style, where the papers were the proofs were based more on geometric ideas, and there was no proper rigor. But then, being a commutative algebraist and field theorist, he developed the necessary commutative algebra and field theory to translate all that into the modern language, and then he was able to rewrite everything gradually and show that everything is can be made rigorous using commutative algebra. So so this is so here is a theorem. So here is a theorem. Let X be a variety. Then and P a point of X, then P is non-singular if and only if dimension over K of MP mod MP squared is equal to dimension of X. Okay, so this is the correct statement. So what I want to tell you about this is, you see, you have the local ring OXP. Okay, this is the local ring of X at the point P. Okay, and it is a local ring, so it has a unique maximal ideal, and that maximal ideal is given by this MP. Okay, so this is with unique maximal ideal MP, right. And now what you must understand is the dimension of the local ring, you know that this is the same as dimension of X. This is something that we already know. Okay, the dimension of the local ring is the same as the dimension of X. and so you can here I can add if I want it if I want to reflect the point P, I can also write dimension of OXP. Okay, and so if I remove the, if I don't look at the central one term, then I have a condition which seems to have only to do with the local ring. I am just saying that the dimension of the local ring is the same as the dimension of M mod M squared. So what I want you to understand is the local ring modulo the maximal ideal will give you just K. Okay, and what you must understand is that if you look at MP squared, okay, this is the square of the ideal MP. So this is just consisting of elements of the form sigma ai bi I equal to 1 to some L, where ai and bi are in the maximal ideal. Okay, this is just the squared ideal, alright, sum of finite sum of products taken two at a time from the ideal, okay, from this maximal ideal MP. And this is, if you look at it, if you look at and of course this is contained in MP, okay, this is certainly contained in MP because if you take two elements of this ideal and multiply them out, the product is certainly in the ideal. This sums, such finite sums are also here. So this is contained inside this. But the point is that if you look at MP mod MP squared, okay, this is a K vector space. Okay, this is a K vector space, and it is a K vector space just because of this fact, because O mod M is K. Okay, so this is a K vector space, it is a module over K. Well, in fact, you see, you take OXP modulo MP, you can define a scalar multiplication like this. By simply F so F bar comma G bar going to F bar G bar, I think this should give you an obvious map which will make MP mod MP squared a module over OXP mod MP, but OXP mod MP is just K, therefore MP mod MP squared is a module over K, so it is a vector space. Okay, so you can you can check that this is this map is well defined, where this F bar is where F is an element of the local ring, so it is a germ of a regular function at the point P, and F bar is its image. Actually F bar is just that regular function evaluated at the point P, okay, it is just evaluation, and here you're taking G bar, G bar is just the image of a G. G is just a regular function in a neighbourhood of P, germ of a regular function in neighbourhood of P which vanishes at the point P. So G is in MP, and its image in the quotient MP mod MP squared is G bar. So you are reading G up to going mod MP squared is just reading only the linear term. When you go mod M, you are evaluating at the point. See, these are all actions that are going on at the with the elements here in the local ring. What are the elements in the local ring? The elements in the local ring are regular functions, germs of regular functions. How do you get this quotient isomorphic to K? What you do is give me a regular function at that point, you evaluate it at that point. You give me a germ of a regular function here, you evaluate it at that point, that will give you a map from this to K. Its kernel will be exactly MP, all those germs of those regular functions which vanish at the point P. So the quotient will be K. So this isomorphism is just evaluation, arises just by evaluation of a germ of a regular function in a neighbourhood of P at the point P, okay. And what is this, what does M mod M squared stand for? It is, you take a function which vanishes at the point P, germ of a regular function which vanishes at the point P, that is what a function that belongs to MP means, and reading it mod MP squared means that you take literally its derivative, because you are cutting, if you read mod M squared, that means you are only taking the linear term, you are not taking the degree 2 term onwards. So in a sense this corresponds to reading only the linear term, alright, and that is correspond, and the first order term always is the derivative. So going M mod M squared is reading of the derivative in a certain sense, okay, and therefore this is how M mod M squared becomes a K vector space, okay, and it is it's certainly a finite dimensional vector space, because after all OXP is a Noetherian ring, this local ring is a Noetherian ring, and this ideal MP in this Noetherian ring is finitely generated. You take a set of generators and take their images here, they will give you generators for this quotient. So it is a vector space which has finitely many generators, and therefore it is a finite dimensional vector space. It is a vector space which has a finite spanning set, so it is a finite dimensional vector space, okay. Therefore this is a finite dimensional vector space, you calculate its dimension, okay, and this dimension, if it is equal to the dimension of X, then and only then is the point P a non-singular point. So what this quantity is, this quantity is actually the dimension of the tangent space at the point P. This quantity, dimension of M mod M squared over K, actually measures the dimension of the tangent space to the variety X at the point P, and what normally will happen is that this will be more than this, as we saw in those examples of a cone and a line and a curve with a kink at a point. What happened at the singular point was that the dimension of the tangent space shot up, the dimension of the tangent space became more than the dimension of the object. For the vertex of the cone, the dimension of the tangent space is 3, whereas the cone is only 2 dimensional, so the vertex is not a smooth point, it is a singular point. Similarly, if you take a line with a kink, if you take a curve with a kink, at the point where you have the kink, the tangent space becomes 2 dimensional, and the dimension is 2, which is greater than dimension of the curve, which is 1. So that point which is the kink is not a smooth point, it's a singular point, okay. So that's exactly what is happening here. So it's a matter of a little bit of commutative algebra to check that if you have a Noetherian local ring with maximal ideal M, then the dimension of this vector space will always be greater than or equal to the dimension of the local ring, okay. And if the dimension is greater than the dimension of the local ring, then that point P is not a smooth point, it's not a non-singular point, it's a singular point, it's a singularity. If the dimensions are equal, then it is a smooth point. So the point I want you to understand is that what this theorem is saying is exactly the analog of what we saw in the analysis calculus situation, that a point of a variety is smooth if and only if the dimension of the tangent space at that point is exactly equal to the dimension of the variety. And what will happen if it is a non-singular, if it is a singular point, this will be bigger than this, you will have more, the tangent space dimension will be more than the dimension of your of the space on which the point lies. Okay, but the nice thing that I want you to notice is that whole thing that is done using calculus, all that has been captured just using local rings, that is what I want you to appreciate. Okay, so when you do usual calculus, how do you define a tangent space at a point? You take a point, you draw a curve through the point, and then you draw the tangent to the curve at that point. Okay, and then like this you try to fill a neighborhood of the point by curves, draw tangents and then now take this all the space of all these tangents, that is the tangent space. So it involves the usual facts from calculus, thinking of curves passing through the point and drawing tangents and all that. Okay, and of course even to find the tangent to a curve at a point, it is a limiting process, right, because you take that point and you take a sufficiently close point and then you draw a chord and then you take the limit as the sufficiently close point tends to the given point, so the chord becomes the tangent at that point. So in the usual calculus, even the process of getting hold of a tangent is a limiting process, and then you, in this way, you build the tangent space, you check out what the tangent space is, you calculate its dimension, and then you check whether the tangent space dimension is more or whether it is equal to the dimension of the object, and then that is how you get smoothness or not, and it involves a lot of calculus. But you see, in algebraic geometry all that limit process is not there, but still you are able to capture the smoothness, the non-singularity. The key is local rings. Okay, that is one fact. Then the other fact is, what this tells you is that this, based on this definition, tells you that this definition is independent of the embedding of x in affine space. If x is an affine variety, then a point of x is smooth. Okay, that is a condition which is intrinsic to the point, because that condition only depends on the local ring at that point, and the local ring at a given point is invariant, it will not change. If you, no matter how you embed your variety, the local ring is an invariant, and therefore this theorem tells you that the non-singularity that you have defined here actually really does not depend on this embedding or this ideal, I mean this embedding which dictates this ideal, and then the ambiguity of what generators you have chosen for this ideal. Okay, so it is a very intrinsic statement. Okay, and that tells you that you do not have to worry about this definition, but it is useful to make calculations and to check that a given variety defined by a bunch of equations is smooth or not at a point. So in that way this definition is useful, but that theorem tells you that you are not going to go wrong if you use this. Okay, so I will give you a proof of this in my next lecture. Okay, so I will stop here.